This is a guided notes video regarding relations and functions. In life, we often have to pair up items from one set with items from another set. For example, at school, there's probably a list somewhere of students paired up with their height. Coaches have a list of players paired up with the number of points they scored in a game. Or there might be another coach that would have statistics with a pairing of the amount of time that was passed for a race and the distance that the runner traveled. So a relation is just a pairing of elements from one set with elements from another set. And one way to show a relation is with ordered pairs. For example, with the students to height relation, I could make ordered pairs like this. Nate is 6'3". Jane, 5'7". Chris is 5 feet 2 inches, and Jose is 5 feet 6 inches. The direction of the relation is important. If you change which set comes first, it's a completely different relation. Relations have a domain and a range. The domain is just this list of all of the input values, which are all the first elements in the ordered pairs. The range is a list of all of the output values, which are the second elements in the ordered pairs. So for example, we have a relation here, a set of ordered pairs. The domain is all of the inputs, the x values, everything that's going in to this relation. So we have 100, 120, 140, 160, 180. That's the list of all of the domain values. The range is everything that's coming out of the relation. The second number's listed, so that would be 5. Notice we have 5 twice. I don't have to write it twice. I only have to write it once. We have a 6. Again, 6 is listed twice, but I don't have to write it twice. And we have a 12. That's the range, the list of everything that is an output. So what is a function? Well, think about a relation where we would have cell phone numbers paired up with the cell phone owners. So look at this relation. Do you see any problem with it? Notice 640-3299, 640-3299. That goes with Jake, but it also is Cindy's phone number. So if I dial that number, who am I going to get, Jake or Cindy? 640-1111, 640-1111. That's Kim's phone number, and it's also Jenny's phone number. That's a big problem. There's more than one output for the same input. You can't do that because I don't know who I'm going to get when I dial the number. I want to know when I dial that number, it's going to go straight to the person I'm trying to reach. So this is not a function. A function is a special relation such that each element of the domain is paired with only one element of the range. There's only one output for each input. If I put in a phone number, it's only going to go to one particular person. Another way of looking at it is the first coordinate is never repeated. When I list those out as ordered pairs, I should never have the same number as the first coordinate. Also, you could say that a function can have the same output for different inputs. It's okay if Cindy has 2 different phone numbers. I can have different phone numbers that go to the same person, same output. I still know who I'm going to get if I dial that number, so that's okay. Let's look at example 2. Is it a function? Well, I want to make sure that there's only one output for each input. 2. If I put in a 2, what am I going to get out? A. That's the only thing I'm going to get out, so it's good. How about 3? If I put in the 3, I'm only going to get an A. How about the 4? If I put in the 4, the only thing that's going to come out for this first example is an A. So yes, this is a function. Notice 2, 3, 4. Nothing's repeated. The second example, if I put in a 2, I'm going to get an A. If I put in a 2, I could get a B. Or if I put in a 2, I could get a C. I don't know what I'm going to get out. Everything is the same. I have the same input listed more than once. So I can see here that this is not a function. Another way to think about it is a pop machine. If you look at this pop machine, is it a function? If I push a button, do I know what's coming out each time? Yes. Each different selection gives me a different pop, and I know what I'm going to get when I push the button. If I push the Coke button, I'm going to get Coke. So that's a function. But what if there were 2 Coke buttons? What if I had a second Coke button over here? We'll pretend it's a bigger machine and there's another Coke. Is that a function? Well, if I push either Coke function, either Coke button, do I know what's going to come out? Yes, I do. So that is a function. It's okay that there's 2 buttons as long as I know what's coming out of it. Coke is coming out each time. What if one of the buttons said Coke or Dr. Pepper? Would that be a function? I don't know what I'm going to get out when I push that button. So that one is a no. Because if I push the button, I don't have a certain output every time. It could vary. Function notation. So we often name functions with letters, like F or G or H, some letter of the alphabet. So if we think about this function f in example 4, it's going to be paired with itself times 2. So if I put in a 1, I'm going to get out a 2. Put in a 2, it's going to be a 4. 3 gives me an output of 6. 4 gives me an output of 8. And in general, any number that I put in will give me an output that's twice as big. We can write that function like this. F of x equals 2x. Now notice what I just said, f of x. That's what this thing means. F parentheses x parentheses. It's just telling me I have a function named f and the input is an x. And then this is the rule that defines that function. 2x. 2 times whatever I put in is what's going to come out. So the important thing is that f parentheses x does not mean f times x. Often in algebra, if we have a letter or a number outside the parentheses, we're multiplying. But in function notation, we are not multiplying. It's just telling me I have the function f and the input value is x. So let's look at these examples. What is f of 2? Well, I know that this means what am I going to get out if I put in a 2? It told me right up here. If I put in a 2, I'm going to get out a 4. So f of 2 equals 4. How about f of 7? Well, I don't have that listed in the ordered pairs, but I can use the rule as well. Remember, the function f just is 2 times whatever you're putting into it. So what I'm putting into it is that 7. I substitute that in for the x. 2 times x means 2 times 7 in this example. So 2 times 7 is 14. Example 5. We want to find f of 0. So I see the rule, f of x equals 8 plus 4x squared. The 0 is my input. That means 0 is going to go in for that x. So I'm going to write it out as 8 plus 4 times 0 squared. Remember, that exponent, that squared, only is applied to the x. It does not square the 4. So only the 0 is going to be squared. 0 squared is still 0. And 0 times 4 is 0. Now I can add 8 to that. And I get 8 is the value that comes out if I put a 0 in. Remember to use the order of operations, PEMDAS. F of negative 2. So now negative 2 is my input. I'm going to put that in for the x. 8 plus 4 times negative 2 squared. So again, order of operations says that I'm going to first do the exponent, and the only thing that's being squared is the negative 2, not the 4. Negative 2 squared means negative 2 times negative 2. A negative times a negative is a positive, so this is positive 4. Be careful if you're putting that into a calculator. Remember, negative 2 has to go in parentheses if you're entering it into the calculator. So now I have 8 plus 4 times 4. Do the multiplication before we add. 4 times 4 is 16. 8 plus 16 is 24. And then we want g of 3.5. G of x is a different function. It is x plus 7. So my input value is 3.5. It's going to go in for that x. Substitute it in. 3.5 plus 7 is 10.5. How can you recognize a function from a graph? Well, let's plot these points. I've got 0, 1, 1, 3, 2, 6, and 1, 1. Well, if you look at the ordered pairs, we recognize this is not a function because I have 1 listed twice as an input. If I put in a 1, I might get a 3, or I might get a 1. That's a problem. It's not a function. So what we have in the graph that shows us it's not a function is that the 1, 1 and the 1, 3 are on the same vertical line. See how they hit the same vertical line there? So anytime there are 2 or more points on the same vertical line in a graph, it's not a function. How can we tell from the graph that it's not a function? 2 points are on the same vertical line. So let's look at some examples where we're using the vertical line test. If we look at this one, and you just Imagine a vertical line that's just sliding from left to right across that function. You want to see, does it ever hit 2 points on the graph at the same time? As I go around, as I go from left to right, it's only hitting 1 point on the red graph at a time. So it is a function. As I look at this example, as I move this vertical line across the graph, you see that it's hitting 2 points on the red graph at the same time, all the way across. So this one is not a function. So what do you think on example 6? Is this first one a function? Look at your vertical line going across. It's hitting just 1 point at a time the whole way across. So yes, this one is a function. Looking at example 2 over here, as I go across, look, I'm hitting 2 points everywhere, 2 different red points. So this one is not a function. Example 7, is it a function? Do the vertical line test. Slide that across, left to right, hitting just 1 point at a time as I go across. So yes, it is a function. We're going to come back to domain and range in a minute. Let's evaluate f of -2. So if I put in a -2, that means x is -2. The x is -2 right here. So what is the y value there? What's coming out if I put in a -2? -4. Let's do f of 1 instead of f of -3. Since there is actually an open circle at -3, I'm going to change this to an f of 1. Because that means at that open circle, that is not a part of our graph. So we're going to look at f of 1. If I put in a 1, I'm right here on the graph. What's coming out there? -4. Now we'll look at the domain. Domain is all the values that can go in. They're all the x values, anywhere on the x axis. So one way to think about it is, what are all the x values from left to right? So if I look at the most left point, it's at that -3, but notice it's the open circle, so the -3 isn't actually included, but it comes close as it can get without touching the -3. On the right side, it goes all the way over to the 1. So on the x-axis, I go from -3 to 1, but I'm not including the -3. So I write that as -3. I'm going to put the x in the middle because I'm talking about x values, and 1 on the right. I go all the way from -3 to 1. X is everything in between there. So I put that less than symbol. On the -3, remember the -3 is not included because of the open circle, so I do not put an equals under it. On the 1, that 1 was included. As we look down here, it was a solid circle, and I can erase that so you can see that. So I need to put the equal sign on that to show that the 1 actually is included in my domain. If it is an open circle, like it was at the -3, don't put the equal sign under the less than. So domain is on the x-axis, range is on the y-axis. I'm going to erase those lines, and let's look at the y-axis now. Range is meaning how far from bottom to top. We start at the bottom and go up to the top. So the point that's the farthest on the bottom is at -4. So I go from -4. I want all the y values that are between -4 and then the highest values at 0 on the y-axis. Again, this time we're looking at the y-axis, not the x-axis. We're looking at all these numbers from -4 on the bottom to 0 on the top. And then I put in my inequality symbols, my less than. -4 is less than all the numbers in that range. 0 and all the numbers in the range are less than 0. I have to decide if I want to put any equals under those. Notice it does touch the -4 here and here. That's included in my range, so I'm going to put the equals. The graph touches at the 0 point. Even though it's an open circle at the -3, the graph is touching at the 0, 0. So I'm going to also include an equal sign over there. And that concludes our notes on relations and functions.